So this is the last of 4 lessons on Chapter 2. We're continuing on page 61. The acidity and basicity of representative element oxides. There's a really good generalization down here that is worth pointing out. The oxides and hydroxides of reactive metals, that is metals with electronegativity less than 1.3, are basic. So which ones are those? Look at the table. Anything magnesium and below in the second group, and all the group 1A metals, they would all be basic. And so the oxides of these are all basic. The oxides and hydroxides of nonmetals with electronegativity greater than 2 are acidic. Let's take a look. Where are the nonmetals with electronegativity greater than 2? Well, pretty much all the nonmetals have electronegativity greater than 2. So all of these nonmetal oxides should be acidic in water. And finally we have here the oxides and hydroxides of metals or metalloids with electronegativity between 1.3 and 2. They're usually amphoteric. So where are the metals or metalloids with electronegativity between 1.3 and 2? Between 1.3 and 2, metals and metalloids, well, pretty much anything in here, right? These are the metalloids and these are some metals. So this whole region should have amphoteric metal and metalloid oxides. What's this mean? Well, an acidic oxide reacts with water to produce an oxyacid. A basic oxide reacts with water to produce the hydroxide ion. And an amphoteric oxide can be made soluble if it dissolves in excess base or excess acid. So we're going to finish up this chapter by writing balanced equations for the reactions of these element oxides in water. Page 62. Let's write balanced equations for the reactions of the element oxides in water, keeping in mind that oxides of reactive metals with electronegativity less than 1.3 are basic. Oxides of nonmetals with electronegativity greater than 2 are acidic, and oxides of metals or metalloids with electronegativity values between 1.3 and 2 are usually amphoteric. So I have taken the electronegativity values from this table and put them opposite each element. In the case of lithium oxide, its electronegativity is 1. Well, that's less than 1.3, so it's basic. What would you predict for the products? Well, it would be the hydroxide of the metal, lithium hydroxide. Lithium has a charge of +1, hydroxide is -1, that's the correct formula. Is the equation balanced? 2 lithiums here, let's put a 2 here. It gives me 2 hydrogens and 2 hydrogens. Yes, that's balanced. In the case of sodium oxide, same electronegativity is less than 1.3. Sodium oxide is basic. It's going to form sodium hydroxide. And we need 2 of this. Now, I'm asking you to memorize these or be able to do this on a test, so I'll kind of check them off as we go. You should be able to do every one that I check. Potassium oxide. Potassium is even more basic than lithium or sodium. Potassium oxide in water produces potassium hydroxide, and that's balanced. Rubidium oxide, much the same as potassium, would produce rubidium hydroxide in water. And cesium, even less electronegative still, even more basic, forming cesium hydroxide. That's the end of the alkali metals. Let's go to the alkaline earth metals. The top of the list is beryllium. Now beryllium, let's go back here and take a look. Its electronegativity is not less than 1.3. In fact, it's between 1.3 and 2.0, and so that's typically amphoteric. In fact, it is. So beryllium oxide is amphoteric. It dissolves in base and dissolves in acid. So I'm not asking you to memorize these equations because they're atypical. They're not normal, but you should be able to balance them. 2 sodiums, let's put a 2 here. 4 hydrogens, there's 2 and 2. Oxygens are 4, that's 1, 3, 4. Looks like it's balanced. Beryllium oxide also dissolves in acid, producing a chloride. Is that one balanced? Almost. You got 2 chlorides, 2 chlorines. Again, so you're not responsible to memorize those. I'm simply showing that beryllium oxide is an amphoteric oxide. It will dissolve in both base and acid. And we'll talk about this polyatomic structure later on in the course. Let's move down group 2A. The next element is magnesium with electronegativity that is less than 1.3, right? That means it's basic, so it will form a basic hydroxide in water, which would be magnesium hydroxide. Now magnesium is +2 oxidation state and hydroxide is -1, so we have to write it MgOH2. And that looks like it is balanced. Below magnesium is calcium, even more basic still. That'll be calcium hydroxide. So yes, you're responsible to be able to predict and balance those equations. Strontium is below calcium. Strontium hydroxide is formed when strontium oxide is put in water. And finally we have barium, also basic, forming barium hydroxide in water. Okay, group 3A. Now boron, with an electronegativity of 2.0, it's on the border between being acidic and amphoteric. Let's take a look. So boron is a metalloid. So in our classification scheme it would be amphoteric, but in fact it is slightly acidic. Boric oxide, oxidation state is +3, is in fact weakly acidic and will form boric acid. And I'm going to ask you to memorize the formula for boric acid because it's so important. H3BO3, we'll be dealing with it in a lab soon. It's such a weak acid that it's sometimes written in this fashion. Almost look like a base written this way. These are alternate formulas of boric acid. Both are correct. This in fact is orthoboric acid, and we'll give more detail to that in an upcoming lab. So I'm going to ask you to memorize that boron oxide in water forms boric acid. Is this balanced? I have 2 borons on the left. I better put a 2 on the right. That gives me 6 hydrogens. We'll need a 3 here. That gives me 6 oxygens, which we have, and that's balanced now. So aluminum with an electronegativity of 1.5. Well, it sits right on the staircase. We know it's a metal by virtue of its properties, but it also has some metalloid characteristic. So it does in fact act as a metalloid, dissolving in base, producing sodium tetrahydroxoaluminate ion. We'll learn how to name these later in the course. You're not responsible to memorize this, but we can balance it. Is this balanced? No, I see 2 aluminums on the left. We better put a 2 here. That means we have 2 sodiums. How about hydrogens? 2 times 4 is 8. So we have 2 here. We'll need 3 more. Put 3 there. And then the oxygens, we have 2 times 4 is 8. 3 and 2 is 5 and 3 is 8. So you don't have to memorize that one, but I think aluminum oxide and HCl would be easy to remember, and I'm going to ask you to do that. It's simply aluminum chloride in water. So is that balanced? No, 2 aluminums and 2 aluminums. 6 chlorides, we better put a 6 here. 6 hydrogens, we better put a 3 here. That gives us 3 oxygens and 3 oxygens, so that is balanced. Gallium, below aluminum, it's odd that its electronegativity increases. It should be going down, but that's probably because of the unique character of aluminum more than it is of gallium. Gallium's probably where it ought to be. Gallium, with an electronegativity of 1.9, is a metalloid. You don't have to memorize these equations, but you should be able to balance them if you were given them. I see 2 galliums on the left. Let's put a 2 on the right. Gives me 2 sodiums. For oxygens, I have 2 times 4 is 8. This is 3 plus 2 is 5. I need 3 more. That would give me 6 hydrogens plus 2 is 8. And 4 times 2 is 8. Looks like it's balanced. Gallium oxide, which I'm not asking you to memorize, it in fact would react with an acid in the same way as aluminum oxide would, forming gallium chloride. Gallium is plus 3, plus H2O, and it should balance exactly the same way as aluminum. It has the same oxidation state. I have 2 galliums, 3 oxygens, 6 chlorides, 6 hydrogens, and 3 chlorides. Indium, further down group 3A, is more metallic than gallium, so it will in fact form hydroxides in water. This is indium plus 3, and so it'll form indium 3 hydroxide. Recall that indium can be plus 3 or plus 1. This is indium 3 oxide forming indium 3 hydroxide. Let's balance that. 2 indiums on the left, 2 on the right. Hydrogens, I have 3 times 2 is 6. I'll put a 3 here. Oxygens, I have 6 on the right, and therefore I have 6 on the left, and that's balanced. Thallium has the same electronegativity as indium, so again it's somewhat basic. It'll form thallium hydroxide. This is thallium plus 3. This is thallium plus 1. So thallium 3 oxide will produce thallium 3 hydroxide. It will look like this. Thallium 3 hydroxide. Let's balance that. 2 and 2. 6 hydrogens. Put a 3 here. 6 oxygens. Yes, that's balanced. Thallium 1 oxide will form thallium 1 hydroxide, whose formula would be written like this. Odd looking, isn't it? We don't put parentheses around polyatomic ions like hydroxide unless there's more than one group of them. Just compare sodium hydroxide, right? It just looks different because the second character almost looks like it's uppercase. Thallium 1 hydroxide, let's put a 2 here, and I think that takes care of it. So I want you to memorize indium 3 oxide in water. It's basic. Thallium 3 oxide and thallium 1 oxide. So those that I'm crossing off with X's you don't have to learn, but the other ones I think are reasonably straightforward. An important note here, note that in acid-base reactions, the oxidation number of the atoms remains unchanged. These are not redox reactions, right? They're proton transfers. So thallium 1 oxide produces thallium 1 hydroxide. Thallium 3 oxide produces thallium 3 hydroxide. And that's really important, as we'll see, in predicting the formulas of the products. Page 63. Carbon dioxide. Now carbon's in group 4A. It has electronegativity of 2.5. Carbon is clearly a nonmetal. Recall that oxides of nonmetals with electronegativity greater than 2 are acidic. So carbon dioxide should be acidic. In fact, it is. Carbon dioxide in water just combines to make carbonic acid. And that's balanced. Going down group 4A, we have silicon next. Silicon has an electronegativity of 1.8. It is amphoteric. Here's silicon right on the staircase. So electronegativity between 1.3 and 2.0 is usually amphoteric, and silicon is certainly that. So silicon oxide, being amphoteric, will dissolve in sodium hydroxide. Now silica actually exists in a polymeric form, and that is glass. Glass is essentially silica. And yes, glass can be dissolved in hot sodium hydroxide, forming sodium silicate. Here's the formula. Now this is one you're not responsible for, but we should be able to balance that. Looks like I have 4 sodiums on the right. Let's put a 4 on the left. Now how about the water? 2 plus 4 is 6 oxygens. Looks like we need 2 here, and that should take care of that. Germanium is next. Germanium is similar in electronegativity to silicon, 1.9. It's less than 2. It's right on the staircase. It's amphoteric. You are not responsible to remember these reactions, but we should be able to balance them. So germanium oxide reacting with sodium hydroxide forms sodium germanate. Don't worry about the name. It's kind of an odd duck. Alright, 4 sodiums. Let's put 4 here. Let's balance our hydrogens. We have 4 and we'll need 2 here. Let's check the oxygens. I have 4 plus 2 is 6. 4 plus 2 is 6. That looks balanced. Germanium oxide in HCl. Strange looking complex. This is called hexachlorogermanate ion. Well, later in the semester I'll teach you how to name these complex ions. We should be able to balance it though. I see 6 chlorides on the right. Let's put 6 on the left. Oxygens, I have 2 on the left. Let's put 2 on the right. Now the hydrogens, I have 6 on the left. Right now I have 4 on the right. I need 2 here. And just as a check, the total charge on the left-hand side is 0. And the total charge on the right-hand side, therefore, has to be 0. So I have plus 2 and minus 2. That combines to make 0. You're not responsible for silica or germanium oxides. Let's move down further. In group 4A we have tin and then eventually lead. Now we can have tin plus 4 or tin plus 2. So this is the inert pair effect we're seeing here. Now all of the oxides of tin are in fact amphoteric. You've seen tin. It is a metal. It's silvery, it's soft, conducts electricity. Its physical properties are clearly metallic, but its chemical properties are amphoteric. Tin 4 oxide dissolves in a base. It's amphoteric, forming this creature, sodium hexahydroxostanate ion. Again, don't worry about the names at this time. In time, you'll be able to name these. Let's balance this. I have 2 sodiums on the right. Let's put 2 on the left. Let's balance the hydrogens. I have 6 on the right, 2 here. I'll need 4 more. That should take care of that. Let's check the oxygens. I have 6 on the right, 2 plus 2 is 4, plus 2 is 6. That looks balanced. Not responsible for that. Tin 4 oxide in HCl forms hexachlorostanate ion. So again, don't worry about the nomenclature for now. We'll get to that later. But we can balance this. 6 chlorides, 6 chlorides. 2 oxygens here, 2 here. 6 chlorides on the left. There's 4 plus 2 makes 2 more, and that's balanced for charge and for mass. The charge is 0 on both sides. So you're not responsible for that either. Tin 2 oxide, it's amphoteric, dissolves in base or acid. What about in base? It forms this sodium trihydroxostanate 2 ion. Looks like it is balanced already. You're not responsible for that. Tin 2 oxide in HCl forms this species. It's tetrachlorostanate 2 ion. You're not responsible for memorizing that, but we can balance it. 4 chlorides on the right, 4 on the left. 1 oxygen here. We have 1 here. We have 4 hydrogens here. We have 2 here. We'll need 2 more. And that looks right. Plus 2 and minus 2 makes 0. Everything's balanced. Okay, finally in group 4A we have lead. And lead can be plus 4 or plus 2. The lead oxides are again amphoteric. They'll dissolve usually in base or in acid. So in a base, lead 4 oxide will dissolve to produce hexahydroxoplumbate 4. Again, we'll learn to name these later on, but we can balance this. 2 sodiums on the right, 2 on the left. Hydrogens, I have 6 on the right, 2, and I'll need 4 more, so there's 2. Oxygens, I have 6, there's 2, 4, 6. That looks balanced now, but you're not responsible to learn that. Turns out that lead 4 oxide does not dissolve in HCl, so it's an exception to the rule, so we'll just move on. Lead 2 oxide, it's amphoteric, dissolves in a base, in this case producing sodium trihydroxo, looks like I left the O out there, plumbate 2. You're not responsible to learn that, and it looks like it's already balanced. And finally, lead 2 oxide in acid forms tetrachloroplumbate 2 ion. Let's see, we could balance that. I got 4 chlorides and 1 oxygen. So I just have to balance the hydrogens. I have 4 here, 2 here. Looks like I need 2 more, and that's balanced for charge as well as mass. Right, so there's a lot of reactions you're not responsible for. That brings us to group 5A, nitrogen. Now nitrogen is a nonmetal, and its electronegativity is greater than 2. Just want to point that out to you. Here's nitrogen. It's a nonmetal. Its electronegativity is greater than 2. So clearly that will be acidic. So nitrogen oxide in water makes an acid. Now I've listed here 2 different oxides of nitrogen. So what acid will they form? Well, let's get the oxidation state. This is nitrogen plus 5. This is nitrogen plus 3. Folks, you really must get comfortable calculating oxidation states. There's no escaping it. Well, let's do this one. If this is not clear to you, make sure that you watch the video called Oxidation Numbers. It's not in the video lecture folder. It's in the basic review folder. It's something that's covered in first semester, but you absolutely must know how to do this. Oxygen is -2. There are 5 of them. That makes a total charge of -10 for the oxygens. Now the charge on the whole compound is 0, and that means the total positive charge must be +10 to offset the -10, divided by the number of nitrogens present, and that gives you the +5. Similarly here, -2 times 3, -6. Nitrogens must be +6. There's 2 of them divided by 2. Each one is +3. You must be able to do that. Okay, so what are the oxyacids of nitrogen? I've asked you to learn those. There's just 2 of them. There's HNO3, nitric acid, and there's HNO2, nitrous acid. How do I know which oxyacid forms from which nitrogen oxide? Recall, these are not redox reactions. In acid-base reactions, we don't have a change in oxidation states. So the oxidation state of nitrogen was +5 on the left. It's going to be +5 on the right. This is nitrogen +5. And this is nitrogen +3. That's how we know which product to write. We simply have to balance it. 2 nitrogens, and I think that's now balanced. Yes, it is. 6 oxygens, 2 hydrogens. And this is 2 nitrogens and 2 nitrogens. Okay, phosphorus. Electronegativity 2.1, it's a nonmetal. Let's take a look. So that phosphorus just barely falls in the nonmetal range with electronegativity just barely above 2.0, so it's going to be a weaker acid than nitric acid. Now notice there are again several different oxides of phosphorus. We've learned that there are several different phosphorus oxyacids. Let's write those out. Recall there are 3 of them. There's H3PO4, phosphoric acid. There's H3PO3, phosphorus acid. And there's H3PO2, hypophosphorus acid. Which one will we choose? Remember that the oxidation state remains the same. So let's get the oxidation states. The oxidation state of phosphorus in P4O10 is minus 2 times 10 is negative 20. Total positive charge is plus 20 divided by 4. Each one is plus 5. So the phosphorus oxyacid should have an oxidation state of plus 5 in this case. For P4O6, we have minus 2 times 6 is negative 12. We'll have plus 12 divided by 4. Each phosphorus is plus 3. Okay, let's look at the oxyacids. What's the oxidation state of phosphorus in H3PO4? It is plus 5, right? Negative 8 plus 3. This must be plus 5, so it totals 0. This must be plus 3, right? Negative 6 plus 3 makes plus 3. And in the case of hypophosphorous acid, that's negative 4 plus 3. This must be plus 1. So what are the formulas of the oxyacids of phosphorus that are formed? In the case of P4O10, it's going to form phosphoric acid, H3PO4. Oxidation state is plus 5. Let's balance that. 4 phosphoruses, 4 phosphoruses. I have 12 hydrogens. I'll need a 6 here. That gives me 16 oxygens. 6 plus 10 is 16. That's balanced. For P4O6, phosphorus 3 oxide, we will form phosphorus acid, H3PO3. Let's balance it. P4, put a 4 there. That's 12 hydrogens. I need a 6 here. How many oxygens? I have 4. 4 times 3 is 12. 6 plus 6 is 12. That's balanced. Arsenic, going to be much the same as phosphorus. Electronegativity is the same. It's going to form analogous oxyacids. So we're going to have H3ASO4 called arsenic acid and H3ASO3 arsenious acid. Oxidation state here is plus 5 and plus 3. Oxidation states are plus 5 and plus 3. We just need to balance this. 2 arsenics, 2 arsenics. 6 hydrogens, 6 hydrogens. 5 plus 3 is 8 oxygens. 4 times 2 is 8. 2 arsenics, 2 arsenics. 6 hydrogens, 6 hydrogens. 3 plus 3 is 6 oxygens. 3 times 2 is 6 oxygens. So that's balanced. So on this page, yes, you do need to know the products of the nitrogen oxides in water and be able to balance the equation, and the oxides of phosphorus and the oxides of arsenic, they follow our patterns very clearly. Page 64. We're still moving down group 5A with nitrogen, phosphorus, arsenic, antimony, bismuth. As we move down column 5A, the elements trend from being non-metallic to semi-metallic or metalloid-ish, and ultimately to metallic. We're looking at antimony and bismuth now. So antimony, it's a metalloid, electronegativity 1.9. It does form a weak acid, antimonic acid. We can write the formula for it. If we know the oxidation state, it would be plus 5. So like arsenic acid or phosphoric acid, it would be H3SbO4, oxidation state plus 5. We'll need 2 antimonies. We need 6 hydrogens, we have that. We need 8 oxygens, and we have that. I'm not going to hold you responsible for that. It's kind of an odd duck. We have Antimony Iii Oxide. We have 2 of those. They are in fact amphoteric, dissolving in base, dissolving in acid. In base, it forms sodium tetrahydroxoantimonate 3. You are not responsible for these 2, but we can balance them. 2 antimonies on both sides, 2 sodiums on both sides. 2 times 4 is 8 hydrogens. We have 2 here. We'll need 6 more. That puts 3 here. Let's check the oxygens. We have 2 times 4 is 8. There's 3, and 2 is 5, and 3 is 8. That looks balanced now. Antimony Iii Oxide in HCl forms tetrachloroantimonate 3. Tetrachloroantimonate 3. We have 2 antimonies, 4 chlorides. Hydrogens, we have a total of 4 on the left. We have 2 here. We'll need 2 more, and that's balanced for charge and mass. Next is bismuth. We have bismuth 5 oxide. We have bismuth 3 oxide. So it's a metal. Electronegativity is not that low. It's kind of in the almost a semi-metal range. What will it be? Turns out that bismuth 5 oxide, the higher oxide, is somewhat acidic, and it's going to form an acid analogous to phosphoric, arsenic, antimonic. It's going to be H3BiO4. Let's balance that, and I'll tell you more about it. 2 and 2 bismuths. We have 8 oxygens. There are 5 here. Looks like I need 3 here. 6 hydrogens. That's balanced. Bismuth 3 oxide is a weak base. In water, it'll form the hydroxide, which I would write as BiOH, taken 3 times. Let's just balance that. 2 bismuth on the left, 2 on the right. Hydrogens, I have 3 times 2 is 6. Let's put a 3 here. Oxygens, 3 plus 3 is 6, and 3 and 3 is 6. You're not responsible for bismuth. We'll talk more about this at the end of the course. The fact that the higher oxides tend to be more acidic than the lower oxides is not something that we want to deal with at this point. So if I gave you the product, you could probably balance the equation, and that's all that's required for now. All right, that brings us to group 6A. We have oxygen, sulfur, selenium, tellurium, polonium. We don't have any oxyacids of oxygen. We have to have some other nonmetal there. We can talk about the oxyacids of sulfur and selenium and such. Let's take a look. Sulfur has electronegativity of 2.5. It's a nonmetal, so its oxide will be acidic. There are 2 different oxides of sulfur. We have sulfur-6 oxide and sulfur-4 oxide. So the oxyacids formed will have the same oxidation state. So what are the oxyacids of sulfur? Well, we have sulfuric acid, which is H2SO4. We have sulfurous acid, which is H2SO3. The oxidation state of sulfur in sulfuric acid is +6, and is +4 in the case of sulfurous acid. So that's how we know what product is formed. Well, it looks like it is balanced. And how about this one? Looks like it is balanced. So those are something you're certainly responsible for. We go down, we got selenic oxide, Selenium-6, and we get selenous oxide. Take a look at selenium. So selenium is still just barely a nonmetal with a electronegativity that's greater than 2. Therefore, it should in fact be acidic. So let's write the acids formed by these selenium oxides in water. So we don't know what the oxyacids of selenium are, but recall that it's in the same group as sulfur. So we can expect it will have the same form, and we'd be right in most cases. It would be H2SeO4, that'd be selenic acid, and H2SeO3, selenous acid. The oxidation state here is +6, like Selenium-6 oxide, and +4, like Selenium-4 oxide. Are these balanced? And in fact, I believe they are. You could learn those. So tellurium oxides are somewhat anomalous in their behavior, so you are certainly not responsible for memorizing these, but since we're dealing with them, let's talk about them briefly. Tellurium-6 oxide is quite anomalous. It forms telluric acid whose formula doesn't look anything like selenic or sulfuric. So I just give it to you there. Looks like that's almost balanced. Let's see, I have 3. I need 3 more oxygens. Put a 3 here. That takes care of it. And tellurous acid well, it will actually form an acid that's analogous to sulfurous or selenous. It would be H2TeO3, and I think that is in fact balanced. Alright, so you don't have to worry about tellurium, it's odd anyway. That brings us finally to group 7A. Fluorine, the most electronegative element on the periodic table. Its behavior is unique. It does not form an oxyacid in water. In fact, it just oxidizes the water that it's in, producing oxygen gas and hydrofluoric acid. It's nasty, nasty stuff. That brings us to chlorine oxides. What's the oxidation state of chlorine in Cl2O7? That's -14. This would be +14 divided by 2. This is +7. How about in this oxide of chlorine? That's -2, chlorine's +1. So what oxyacid would we write? These are in fact nonmetals with a very high electronegativity, greater than 2. They'll form oxyacids in water. We are familiar with 4 oxyacids of chlorine. You've memorized the formulas of perchloric acid, HClO4, chloric acid, HClO3, chlorous acid, HClO2, and hypochlorous acid, HClO. The oxidation states in this are +7, +5, +3, and +1. So which oxyacid is formed from chlorine 7 oxide? Well, that would be HClO4, perchloric acid. Is this balanced? Well, no, I got 2 chlorines. How about now? 2 hydrogens, 8 oxygens. That's correct. What about the oxyacid formed from chlorine 1 oxide? Well, it would have to be hypochlorous acid, HClO. We'll need 2 chlorines, and I think that's balanced. So certainly you're not responsible for fluorine, but chlorine oxides you are. For bromine, we have actually 4 different bromine oxides here. Let me just quickly say this is bromine 7, bromine 5, bromine 3, and bromine 1. What are the oxyacids formed from bromine? They'll be HBrO4, perbromic acid, HBrO3, bromic acid, HBrO2, bromous acid, and HBrO, which is hypobromous acid, in which the oxidation states are +7, +5, +3, and +1. And notice the bromine 7 oxide forms the oxyacid with an oxidation state of +7. Let's balance this. We'll put a 2 here, and I think that would be balanced. And a 2 here, that should balance that. And a 2 here looks like that's balanced as well, 4 oxygens, and 2 here as well. So certainly responsible for the products of the bromine oxides in water. And the last one here is iodine. Iodine has an electronegativity of 2.5. It is a nonmetal. What are the oxyacids of iodine? Well, same as bromine and chlorine, we could have periodic, iodic, iodous, hypoiodous. This is iodine +5. So what oxyacid is formed? It would be HiO3, in which the iodine is +5, and that's called iodic acid. To balance that, I think we just need a 2, and you must know that as well. So just to recap, you should be able to complete the equations and balance them for the oxides of the elements in water, for those that I've checked off, those that follow the normal pattern. Those that are exceptions, and I've marked with an X, you're not responsible for, but you should be able to balance the equations. So those were pretty simple rules, and they work in most cases. That brings us to our last page, the hydrides of the elements. Let's look briefly at the acidity and the basicity of the element hydrides. We just looked at the oxides. We won't spend too much time here. Many binary compounds, that's compounds made of two different kinds of atoms, many binary compounds are called hydrides. Generally speaking, the S block metals form ionic hydrides, beryllium and magnesium excepted. These are not ionic, they're still basic, but they're not ionic. P block elements produce covalent hydrides, and going across a period, there's a transition from ionic hydrides, like sodium and calcium hydrides, to covalent polymeric hydrides. In fact, beryllium and aluminum hydrides are actually polymers. They're longer than usual compounds. And ultimately to covalent molecular hydrides, like water and ammonia and phosphine. These are singular molecules. The hydrides of S and P block metals here are basic. For example, sodium hydride in water produces sodium hydroxide and actually reduces the water, producing hydrogen gas. And elements whose hydrides are basic are shaded light gray in this table. The hydrides of some nonmetals are acidic. You're certainly familiar with the hydride of chlorine, hydrochloric acid, hydrofluoric, hydrochloric, hydrobromic, hydriodic, and hydrosulfuric acid. Well, these in fact are acidic. They react in water to produce hydronium ion. Elements with acidic hydrides are colored dark gray in the table. But some hydrides of nonmetals are neutral. You're familiar with, of course, the hydride of oxygen, which is water. It's quite neutral, as is the hydride of carbon, methane, and other hydrocarbons. They're quite neutral. Elements with neutral hydrides are not shaded in the table. Now, the hydride of the nonmetal nitrogen is an exception. The hydride of a nonmetal would typically be either acidic or neutral, but in fact, in the case of nitrogen, it's basic. There are no hydrides of the noble gases at all. What about the transition metals? Well, the number of transition metals, particularly the lanthanides and actinides, absorb hydrogen, giving metallic hydrides, some of which are basic. Now, transition metal hydrides are interesting. They have many properties of metals. They have similar hardness, electrical conductivity, and luster. They look like metals, but unlike metals, they are brittle. Furthermore, these hydrides are non-stoichiometric in their composition. For example, palladium hydride 0.6 to 1 hydride to metal ratio, kind of odd. Vanadium hydride 1.6 to 1 hydride to metal ratio. These hydrogens are in the interstices, or the gaps between the metal atoms. So they're unusual, and that's all we'll say about them. And that brings us to the end, finally, of Chapter 2, which is a general overview of the periodic table and a lot of basic properties. Next, we'll go to a unit on bonding, which I think will be more interesting, at least I find it so. On the next page is a test summary, which is somewhat out of date. I will post a current, up-to-date test summary on Blackboard before each test, including this one. And that'll be it for Chapter 2.